Trends in ionization energy. The general definition of ionization energy is minimum energy required for complete removal of one mole of electron, not one electron only, one mole of electron from one mole of gaseous atoms or gaseous ion. This is general definition, so you don't know whether it's from atoms or ion, and both must be in gaseous state. The specific definition: first, ionization energy, minimum energy required for complete removal of one mole of electron from one mole of gaseous atom. Because this is the first time you remove the electron from atom, that's why it's from one mole of gaseous atom. Energy required, so the delta E must be positive. If energy released, delta E negative. Example, sodium gas atom, remove one mole of electron to produce sodium ion in gaseous state, and the delta E value is positive. Second ionization energy means the second time you remove one mole of electron. The second time you remove, you must remove from gaseous ion, because the first time you remove from gaseous atom and it produced ion, and then the second time it's from ion. Okay, minimum energy required for complete removal of one mole of electron from one mole of gaseous ions. So gaseous ion must be charged positive 1 because you already remove one mole of electron, so it becomes positive 1, the ion. And then when you remove the second time, so it means you already remove 2 mole. So ion 2 plus 1 mole of electron, and again the delta E must be positive because it is energy required, not energy release. If energy release, delta E negative. Trends in ionization energy. So down the group from top of the periodic table to the bottom of the periodic table, down the group, the atomic size, we know it increased because we know the principal quantum number increased, as we said previously in the previous lecture. We know that down the group size increased because the principal quantum number and shielding effect increased. So the distance between nucleus to outer or valence electron increase because you have more and more n. So the distance becomes further and further. The nucleus electron attraction weaker, so easier to remove outer or valence electron because the valence electron become further from the nucleus, so the attraction become weaker. Less energy needed to remove electron, so first ionization energy decreases down the group. So the energy required to remove the valence electron down the group, the energy required to remove the valence electron decreases because you have more and more principal quantum number, you have more and more shell because the shielding effect keep increasing. So that's why your first ionization energy decreasing down the group. When you look at across a period, from left to right of the periodic table, across a period, the atomic size decreases because the proton number increases. So the effective nuclear charge increases. The distance of nucleus to outer or valence electron decreases. Nucleus electron attraction stronger, so it's difficult to remove the outer or valence electron. If it's difficult, you need more energy to remove the valence electron. So that's why across a period, the first ionization energy increases. Anomalies in ionization energy. So this is, we look at when across a period. We know that across a period, previously across a period, first ionization energy increases. So it will keep increasing across a period. From lithium to neon, across period 2, it's supposed to be keep increasing. But you see anomalous cases, 2 anomalous cases here, Be to B and O to O. First ionization energy of B supposed to be higher than the first ionization of Be because it's across the period, because B position is on the right of Be. Across a period from left to right, so B, the position of B is right Be, and position of O is on the right side of N. So B ionization energy supposed to be higher than Be. O first ionization energy is supposed to be higher than N. But in this case, the first ionization energy of B lower than Be, and the first ionization energy of O is lower than N. This is because if we look at the electronic configuration, so here between group 2 and group 13, okay, group 2 and group 13, group 2 for Be in group 2, and for B, group 13, okay, so we are comparing Be in group 2 and B in group 13. The first ionization energy of B is supposed to be higher because it's on the right, but this is less. First ionization of B is less than Be, because if you look at the electronic configuration, 2p subshell is at higher energy than 2s subshell. B has 2p subshell, but Be doesn't have 2p subshell. So the 2p subshell in B is higher energy than 2s. So when this is in higher energy, less energy required to remove single 2p electron. Because we know that the definition of ionization energy is minimum energy required. When the energy of B is already high, you don't need more energy because you already have high energy of 2p, so you don't need more energy. So that's why only less energy is required to remove the electron in B, because it already has high energy in 2p. Okay, less energy required to remove a single 2p electron in B than to remove electron from 2s of Be, because 2s energy is lower than 2p energy. We learned previously the energy in 2s is lower than energy 2p. Energy 2p is higher. We know that the definition of ionization energy is minimum energy required. So you required energy to remove the electron. When you already have high energy, you don't need more energy. That's why the minimum energy required is less in B to remove compared to Be. Okay, that's an anomalous case for Be and B between group 2 and group 13. And another between N and NO, N and O, okay, between group 15, N in group 15, O in group 16. When you compare these two, both have 2p subshell. Okay, if you write the electronic configuration, both have 2p subshell. But in N is half-filled 2p orbital, 2p3, half-filled 2p. O, 2p4, partially filled. So we know that half-filled is more stable than partially filled. So more energy required to remove an electron from more stable 2p. So you need more energy to remove the electron in 2p in N atom. Less stable oxygen, 2p4, less stable because only partially filled, so less energy required. Here N, more energy required. That's why you look at the trend. The first ionization energy of N is higher than first ionization energy of O. Successive ionization energy. First ionization energy less than second ionization energy, less than third ionization energy, less than fourth ionization energy. It's less than fifth ionization energy, it's less than sixth ionization energy, and so on. The electronic configuration of an element and its position in the periodic table can be identified based on successive ionization energy. So you can know the position of atom or element in periodic table by having their successive ionization energy data. Successive ionization energies increase because each electron is removed away from an ion with a progressively higher positive charge. So if you want to remove the second electron you want to remove it, it's harder and harder because the positive charge is constant, but you remove electron, more and more electron, but the number of proton remain the same, but you keep removing the electron. So that's why the successive ionization energy increase. Sudden increase in ionization energy means electron is removed from the inner shell. Okay, example, Be atom in gaseous state to become Be plus in gaseous state. So this is the first ionization energy. This is the electronic configuration of Be atom, 1s2 to s2. You want to remove one electron, so 1s2 to s1. This is the electronic configuration for Be ion. And the ionization energy required, so that's why it is positive 900 kilojoule per mole, because you're removing 1 mole of electron. Alright, this is the second time you want to remove the electron. Second times means you remove from the Be plus, because the first time you remove from atom, second time you remove from ion. Okay, the second time you remove electron into S. Again, the first time remove electron into S, second time remove electron into S. Second ionization energy is higher than the first one. Okay, but if you look at the third removal of electron, okay, this is the third time you remove from Be2 plus. The third time, the third electron you remove from 1s, you remove from n equal to 1. First time you remove from n equal to 2. Second time you remove from n equal to 2. But third time you remove from n equal to 1. The position of electron that you want to remove is closer to the nucleus compared to the first and second time you remove. The position of electron is closer because this electron is at n equal to 1. This 2 electron is at n equal to 2. So it's further. So this one, it's closer. If you look at the third ionization energy, it's very large. It's 14,000. First time 900, and then second time probably double, 1,760. So you can predict it's just double as the first time, second time. Third time supposed to be triple, but this is not triple. This is sudden increase. So we know that when there is sudden increase, you know that the electron is removed from n closer to the nucleus, the n value which is closer to the nucleus. So this is how we know that electron is removed from different n from before. The fourth time, probably double this value, so 21,910. So this from 14 to 21,000 is not sudden increase. It's like double the value. So this is not double, this is extreme sudden increase. So we know that it is removed from different principal quantum number. This fourth is still removed from n equal to 1. The third removed from n equal to 1. The fourth removed from n equal to 1. That's why the value is like double. Okay, this is how you know where the electron is removed, by looking at the data of successive ionization energy. Okay, if you look at the lithium, 1s2 to s1, 500, first ionization energy 500, second ionization energy, try to multiply by 2, so probably 1000, second 1000, but it is 7000. So if you look at the sudden increase, you know that the second removal of electron is not from the same n. See, you have first electron you remove from n equal to 2. Second electron you remove from different n equal to 1. Second electron. That's why second ionization energy is very large. Okay, third electron just times by 2. Around 7,000 times by 2, around 14,000. Here 11,000. So more or less. Okay, so this is, you know that if you remove the third electron, you remove from the same n as before. So here remove from n equal to 1, here remove from n equal to 1, same n. So this is sudden increase, so you know that this electron is removed from different n from before. Okay, Be. first ionization energy, you remove first electron from n equal to 2. Second ionization energy, double, so 900 times 2, around 1800, more or less. Okay, more or less. So means second time you remove the electron, you remove from the same n. Correct. Okay, from the same n. First from n equal to 2, second electron from n equal to 2. So that's why the value is like double the value from before. And then you want to know the third electron. If the third electron you remove from the same n, if the third electron you remove from n equal to 2, this value must be double of this, more or less. So around 1800, 1700, around 3000 something. But this is not 3000 something, this is 14,000. So this is sudden increase, very big gap. So sudden increase, you know that the third electron is removed from different n. Okay, from different n means the third electron removed from n equal to 1. Same goes to B. Okay, B, first ionization energy removed from P, second ionization energy removed from S, but still same n. Okay, n equal to 2, n equal to 2, still same n, but the fourth electron here, fourth electron you remove from n equal to 1. So this is a sudden increase. Alright, so we know that the electron is removed at the inner shell when you look at the data of the sudden increase in ionization energy. That means the electron is removed from the inner shell, different number of n. From the successive ionization energy data, we can identify number of valence electron and group number of the element. Okay, so we have ionization energy 1, first ionization energy, electron removed from 3p subshell. Example, this for silicon, this is the electronic configuration. Okay, this is the electronic configuration. First electron you remove from n equal to 3, second electron remove from n equal to 3, third electron you remove from n equal to 3, fourth electron you remove from n equal to 3, and then fifth electron you remove from inner shell, which is n equal to 2, different number of n. So that's why sudden increase at fifth ionization energy, because fifth electron you remove from different shell from before. Okay, and then you will see another sudden increase when you remove electron at n equal to 1. So from here you can know the number of valence electron. If you look at the trend, look at first, second, third, fourth electron, there is no sudden increase in first, second, third, fourth, and sudden increase in fifth. It means you have 4 valence electron, because at the fifth it is inner electron, so you know that you have 4 valence electron. Okay, when you know you have 4 valence electron, you can know the group of that, because you know the number of valence electrons, so you can know the group of the atom. Sudden increase in ionization energy of 4 from fourth ionization energy to fifth ionization energy means the fifth electron removed from the inner shell, okay, at n equal to 2, because n equal to 2 is closer to the nucleus compared to n equal to 3. That's why it is harder to remove the electron. So much greater energy needed to remove the electron in inner shell. So we know that this is 4 valence electron in here, 4 valence electron, because you have no sudden increase in first, second, third, fourth, no sudden increase. So you know these 4 are valence electron. So 4 valence electron, group 14. Okay, 4 valence electron, group 14. And valence electronic configuration 3s2, 3p2. Okay, and then why group 14 not group 4? Alright, this is because group 4 has valence electronic configuration 4s2, 3d2. Sudden increase of ionization energy can be seen in third removal, because if it is group 4, the first electron that you remove from 4s. Second electron you remove from 4s. The third electron you remove from 3D. So the third electron, you must have sudden increase in the third ionization energy because you remove at n equal to 3. You remove at the inner shell. So you must have sudden increase at third ionization energy if it is group 4. Okay? If it is group 4, this is the electronic configuration. Because we know group 4 involve s orbital and d orbital, and this is the electronic configuration. Sudden increase of ionization energy can be seen in the third removal, because third electron you remove from n equal to 3. Okay?